All right, we're nearing the end of this summer assignment, and I know all of you have worked very hard. Keep in mind that this video should be following your completion of the guided reading assignment for lesson 14.4. This video in no way replaces that, but only kind of enhances it or supplements it. So you should have done that reading first and taken those appropriate notes and read carefully those examples that you were asked to note and read. So continuity is our next issue, and this is really one that's generally set up for calculus and kind of put off until you study calculus. So as we will be doing in not that much time, we can get introduced to continuity at this point. Informally, first of all, what we mean is that if you look at a graph, can the graph of a function be drawn at or near a particular point without lifting your pencil from the paper? And if you look on page 936 and pages 936 and 937, you can see that there is on page 936 figure 14.4-1, on 937 14.4-2. All of the functions drawn on figure 14.4-1 are continuous at that point c comma f of c, whereby on page 937 14.4-2 at the point at the value x equals c, because you can see that in one of the diagrams there is no point at a couple diagrams, a couple of functions, there is no point at c, the last two, c and d. Those are not continuous, or they are discontinuous at x equals c. Well, of course, in mathematics we can look at things informally, but we always come up with a formal definition of continuity, and that is found on page 939. I know you noted it. I wanted you to note it. It's a very important definition, one that we'll see again once we start the school year. But basically, there are three conditions for a function to be continuous at a value x equals c. All three of these conditions have to hold. So the function has to be defined. The limit, so this is why really continuity is kind of put off until we understand the concept of limit. The limit of the function must exist as x approaches c. And the two are tied together in this third requirement, which is that whatever you get for 1 has to equal whatever you get for 2. Now, if either of these things, if f of c is not defined, or f of the limit does not exist, then there's no chance in checking, no reason to check 3, because if something doesn't exist, if that value doesn't exist or it's not defined, it can't equal anything. So all three of these conditions have to hold for a function to be continuous. So let's take a look at a figure that's at the top of page 939. You looked at it when you did the reading, but this illustrates very nicely the three conditions that have to hold. If we look at a, as x approach at x equals a, notice that one is not continuous because f of a is not defined. So we'd say that the function is discontinuous at x equals a. At b, it's also discontinuous because the limit, as we know now, doesn't exist. Now the left-hand limit exists and the right-hand limit exists, but because those are not the same value, the limit itself as x approaches b does not exist. Thus, no chance on continuity there. And lastly, at x equals c. We look over here. Yeah, sure, the left-hand limit exists, the right-hand limit exists, the function exists at x equals c. However, the limit as x approaches c and the value of f of c are not the same. And I think you'd agree with me that, and go back to the informal definition in all three cases, you'd have to lift your pencil to really accurately represent these functions at each of these places what we've discussed. At a, you kind of have to show the existence of the whole. At b, you kind of have to show that little quick drop, that point of discontinuity, and at c, you surely have to lift your pencil to do that. So this definition's worked fine. It's held up over the years. It's a great definition, and one that we'll be looking at, as I said, when we get into calculus. Well, now that we've looked at left and right hand limits, we can really explore what it means to be continuous from the left or the right. And on page 941, the concept is kind of defined: continuity from the left and from the right. First of all, from the right, as long as the value of the function is equal to the right-hand limit, and from the left, as long as the value of the function is equal to the left-hand limit. Figure 14.4-5 at the top of page 941, shown here, illustrates this very nicely. This function, we would say, is continuous from the left because if we get closer and closer to a from the right, this is continuous from the right because if we get closer and closer to a from the right, the limit of it is equal to the actual value of f of a. Likewise, for this function here, it has an endpoint at b f of b, and we'd say it's continuous from the left because as you get closer and closer to b from values less than b, that number that it's approaching, that limit, is equal to the value of the endpoint f of b. When we want to look at continuity on an interval now, it's defined on page 942. To be continuous on an open interval, it just has to be continuous at every point there. To be continuous on a closed interval, then it has to be continuous at every point in the open interval, and it has to be continuous at the endpoint, at the endpoints. So this example 3, which is one that additional example 3, you haven't seen this one yet, you saw an example 3 on page 942. Here's just another graph. If we wanted to explore the continuity of this function, we'd want to probably look first of all at x equals -1. As you can see, since, again, probably in the back of your mind you're thinking, do I have to lift my pencil to draw this? And you do. But really the issue here is that it's discontinuous at x equals -1 for the following reason. The left-hand limit does not equal the right-hand limit, thus the limit doesn't exist at x equals -1. In between -1 and 2, it appears to be continuous. At 2, something weird happens again. We've got quite a drop here. We can see the left-hand limit and the right-hand limit aren't equal to each other, so the limit doesn't exist there. So in summary, if we were kind of talking about how would you describe the continuity on an interval, we would say it's discontinuous at the 2 places it is, which is at -1 and 2, but it's continuous on the following intervals. Now if we look at these intervals, you can see, remember our notation for interval notation is these brackets represent closed intervals. So from -4 all the way to -1, it is continuous. Because again, at these endpoints represent no big gap. And then we'd say at -1 to 2, open interval, it's continuous. And then for values greater than 2, this is how we express this, remember, in this interval. We write it this way, but we wouldn't say 2 to infinity. We'd say for values of x greater than or equal to 2, it's continuous, or it's continuous for all values greater than 2. That's how you would describe it as when you describe intervals. So again, stating the points of discontinuity and then stating the intervals, whether they're open, closed, or half open, half closed, where the function is continuous. And again, we're not hitting all the points of this lesson because of time constraints with this video, but we do have, we'd be wrong not to mention the intermediate value theorem. The intermediate value theorem, which you wrote, is found on page 944. It talks about and look at the language, you can see why we waited till now to talk about the intermediate value theorem. If a function f is continuous on a closed interval, and k is any number between f of a and f of b, then there exists at least one number c between a and b such that f of c is equal to k. So the hypothesis of this theorem uses the concept of continuity. So it needed to be defined. This is a very powerful theorem and used to help find zeros, and we'll probably wait till one of our first days in school in the fall to look at how that works with the intermediate value theorem. But For now, let's just look at this graph. Again, this theorem is what we call in mathematics an existence theorem. And what that means is that the theorem doesn't kind of identify particular values, but only speaks to the existence, that you can find a value which something happens. So again, what we do is with this theorem is we start with a continuous function, and you can see we have one here. This is a continuous function. And we look at an interval from a to b, and we can see that as long as we have a continuous function, then any horizontal line between f of a and f of b will hit the graph at some value c that's between a and b. And you say, well, geez, that will always happen. As a matter of fact, the theorem is an existence theorem, so it could happen more than once. And this diagram shows a case where there are three numbers, C1, C2, and C3, all between A and B. So the value for C will always be between A and B. So if you look at A, it gives us f of A. B gives us f of B. If you pick any number between f of A and f of B, so we arbitrarily choose K, and draw a horizontal line, this horizontal line intersects the graph of f being a continuous function from A to B, 3 times at C1, C2, and C3. So remember now the theorem says that there exists at least one number C, in this case 3, between A and B, such that the value of the function there will be that value for K that you've chosen arbitrarily. When does it not happen? Well, here we have a case where I can choose a value K. So if f is not continuous on the closed interval A to B, there may not be a number C for every choice of K. So I'm going to make a choice that's going to make this not work. I'm going to poke a hole in this argument and say, well, I could have chosen K to be down here and it would have worked, or right here just below f of B. But notice, since I can choose a value for K and be a counterexample to the theorem, and it shows that this is a case where the theorem doesn't hold. So K is right here. Notice there is no value for C that will make f of C equal to K. So that's the intermediate value theorem. Again, it kind of leads to a what's called the bisection method of finding zeros for a function, which is actually used on your calculator every time you find a zero, but we'll look at it more when we get into school. Next up for you, I guess, is exercises in 14.4. It's assignment M. And here they are. Remember, you are going to check your odd answers in the back of the book. Complete them all, but check your odd answers for correctness in the back of the book. And submit your evens so that I can see how you've done. And then next up will be the guided reading for lesson 14.5, then the video to follow, and then some exercises. And then the last assignment Q, which will not be one that you'll submit, but one that you'll bring to school, will be the review exercises on page 961, 1 through 14, and 17 through 28. Again, if you have any questions, email me at jaudet@wocsd.org. Email me if you have any questions or concerns, and we'll try to make things make a little bit more sense to you.